Welcome back to Non-Equilibrium Thermodynamics. This is class number 11. We've been talking about statistical mechanics in classes 9 and 10. I'll do a short little recap here, and then we're going to um, switch to a slightly different lane where we talk about problems where the energy levels are continuous. And so some of you were asking, well, how realistic are the current models if there are only discrete energy levels? It turns out they're used in a lot of cases, and so or at least a few important cases, let me put it that way. And so I thought one thing we could do is a little calculation where I show you how the even this discrete energy levels calculation or assumption can derive a very important model of mixing. So yeah, that may be something nice to do. So as in terms of a recap, what have we been doing? So we've been interested in systems where we have n non-interacting particles. This number n can be really large, really huge, like 10 to the 23rd power number of particles. Um, And so it's going to be fine at some point for us to think about these as being as n being a continuous variable and for the n sub j's to be continuous as well. In any case, large number of non-interacting particles with exactly r accessible discrete energy levels. Then the Gibbs entropy we defined, and we how did we do this? We started out by using counting arguments, and then we used Stirling's approximation to we started with Boltzmann's entropy, which is a kind of counting entropy, and converted this to the Gibbs entropy. So the Gibbs entropy we defined is exactly this: minus K Boltzmann, the sum over the states J equals 1 to R. Those are the accessible energy levels. Nj, that's the number of particles in state J or energy level J, log of Nj over N. So Nj over N, this is a number of particles in state J or energy level J divided by the total number of particles. So this is a fraction, and it's a unitless fraction at that. So that's what explains this minus sign here, because the log of this number is going to be negative, but so the entropy in total should be positive. And of course, we are interested in maximizing the entropy to find the equilibrium state. Well, this entropy is maximized by the so-called Maxwell-Boltzmann distribution function. So the Maxwell-Boltzmann distribution function tells you at equilibrium how many particles are expected to be in state J for J equals 1 to R. So that function is, or that number is the exponential function of minus uj. That's the only dependence there on J. This is the jth energy level. And again, this is positive. K Boltzmann is positive, and temperature also we expect to be positive. So this number works out to be negative. We take the exponential of this negative number. Um, right. So what else do we notice here? Again, the only dependence here on J is through these energy levels UJ. So if the energy is continuous, then this should be how we get this continuous dependence on energy levels. We said before, we had before that there was a parameter here called beta. This beta parameter was a Lagrange multiplier, and it wasn't clear that this Lagrange multiplier would be related to anything. We said, well, the best thing you can say about it is that it can be solved for uniquely, and it should depend on the total energy and the total number of particles, U and N. But then we showed that if I do a couple of manipulations, this beta can be related to 1 over the temperature. In fact, it is 1 over the temperature. Now, the temperature function itself becomes a function of U and N. Okay, so it's a function of U and N, as I'll remind you in uh, repeatedly during these calculations that we do in statistical mechanics. So Z here is a normalization factor, and it's normalized so that if I sum over all of these J energy levels, J equals 1 to R, I get exactly N. Okay, so this constraint here is the mass constraint, and this holds for this Boltzmann distribution. Z is our normalization parameter, and it's called the partition function. And you can think about it as a function just of t, but if you think about t as a function of u and n, then it's ultimately a function of u and n as well. Simplest way to do this is to just think about it as a function of t. And again, it's a normalization factor just so that we get the conservation of mass. The conservation of energy is this equation here, and uh, that's how we or what we use to find out what beta is. So we use this to calculate that beta was equal to 1 over the temperature. Now the energy levels UJ, J equals 1 to R are fixed. They're set in stone. They're fixed energy levels. And the only way that the total energy can change is for um, the the particles to redistribute themselves amongst the energy levels. These things are set in stone already. So you might ask yourself, well, what happens in the case where there are an infinite number of energy levels? They're still discrete, but there are an infinite number of them. This happens all the time in quantum mechanics. For example, if you remember studying the harmonic oscillator in quantum mechanics, then the energy levels are discretized. There's a ground state energy, and then there's a next higher energy, and so on. The energy levels go up off to infinity, um, but um, but in this case, we're only considering a finite number of energy levels. The energy levels in that case that I just mentioned, the harmonic oscillator, they're just still discrete. They're still discrete. So in some cases, you may want to take this upper limit to be infinity. Now, if I have a finite number of particles, then they can't really distribute themselves across a infinite number of energy states, and so some of these numbers are going to be zero, obviously. All right, so all of the thermodynamic variables are given in terms of the partition function. This is something that we observed in the last two lectures. We defined what we mean by the usual Helmholtz free energy in terms of the entropy, the equilibrium entropy, and the energy, and of course the temperature. And we showed that the Helmholtz energy, if I can view this as a function of temperature and N, is just minus Nk Boltzmann temperature times the log of the partition function, which is a function of temperature. So this is a clearly can be made into a function of temperature. It relies on the fact that when we have a temperature relation like this, I can always invert this relationship so that I can rewrite this as u as a function of t and n. So this relation we argue is invertible, and I'll show you this in a lot of cases actually, or at least a few important cases. Let me say that. So whenever I see a relation like this, I'm just going to automatically assume, at least in the context that we're working in right now, that this relation can be inverted so that I can get u as a function of t and n. So make sure that that's clear in your mind. We're going to bounce between t and u a lot, and eventually I'm going to, because it's just going to be too hard for us to keep track of it, I'm going to drop the tildes um, because it just gets a little bit too hard to maintain the tildes and to think about, did I put a tilde here? Did I? So we're going to drop those eventually. Now, in terms of the partition function, the total energy function can be written like this. So this was a relation that we derived last time. N K Boltzmann temperature squared, and the temperature derivative of the log of the partition function. One thing I want you to keep in mind here is the partition function is completely unitless. So this stuff inside of here has no units. That makes sense because we're applying a transcendental function to that. So the units here are energy. The units at the top are energy. So if I take the exponential of that, it's a unitless number. I add those unitless numbers up, I get something which is unitless. So the partition function is entirely unitless. That's that's interesting. We'll keep examining that property as we go along. But it's important that if we're applying, found a mistake here. It should be log. I'm writing log for the natural log instead of ln. Okay. Again, so the total energy can be written in terms of the partition function. The free energy can be as well. And the equilibrium entropy can be written in terms of the partition function. Okay, so partition function, partition function. Remember again, the partition function is a function, at least in this case, of the temperature, just the temperature. And finally, we can show that the chemical potential is also a function or can be written in terms of the partition function. Now, this is all in the context of n non-interacting particles with exactly r finite number of discrete energy levels that are accessible. We're going to see that these calculations, more or less, um, are the same or these relations are much the same in the case of continuous energy levels. So that's the next topic. What happens if we have continuous energy levels in our system? Um, so what is this? And then what does this look like? So suppose we're operating in the same context again, or similar context. We have n non-interacting particles, but the energy of each particle is no longer going to be discrete. It'll be a continuous function of certain variables. What variables are the most important ones? Well, in statistical mechanics, the most important variables are the position vector and the velocity vector. And some people sometimes write this as the position vector and the momentum vector. We're just going to keep it as simple as possible. Position and velocity. And notice that it's a continuous function. So this function here is called the energy per particle or the per particle energy. Okay, so each particle in the system has its own energy associated to it, and it's given by this function. Now, what are the components of the function? So there's two components. The first one is what we call the kinetic energy, right? You probably remember this from your elementary physics course. 1/2 m magnitude of v squared, sometimes called the speed squared. M is the mass of the particle. This is called the potential energy of a particle. And this is given by some externally applied field, which doesn't change with the rearrangements or distribution of the particles in the box. Okay, so we have a box of n non-interacting particles. Per particle energy is given by this very simple function. X is our position vector inside of our domain omega. So we're thinking of the simplest possible case. This is a square box in 3 dimensions, and its side lengths are L, for example. V is our velocity vector. So inside this box, these particles can be going traveling in any one of 3 directions. And the way that we're going to think about them is they don't interact energetically, but they can bump into each other. They can have elastic collisions with particles. And after they have a perfectly elastic collision, they just fly off in the opposite directions, or they can collide with the walls. And the collision with the wall is also going to be completely elastic. Now, that can be identified or built up in this potential energy. And the way people do this sometimes is they say, well, okay, the potential energy is exactly zero inside the box, but if you hit a wall, that potential energy shoots up to infinity. And everywhere outside the box, the particle, the the potential energy per particle is equal to infinity. So basically, this says that it's just a way of saying that the particle cannot get outside of the box, and anytime it collides with the box or the wall of the box, it's a perfectly elastic collision that just throws it back inside. So that's one way of thinking about this guy as a potential energy. Now, this energy per particle, um, it's so where is the non-interacting, where is the assumption that the particles are non-interacting, and how is it built in? Well, it's built into the fact that we're just going to assume that this is the only energy of the system. And the fact that the particle is in a certain energy state has no bearing on whether or not another particle is in some other energy state. And so what I mean by that is, or in one particle in phase space doesn't affect the energy of another particle in phase space. So how does this work? Well, normally, if it were the case that they were interacting, then they would have an energy called a potential energy between the two, or uh, what's the right term for this? This is interatomic potential energy. So the potential energy would want to know, well, what is the position of this particle in space and what is the position of this particle? And if they're close, then the potential energy might be have a force of attraction or repulsion or something like that. So in this case, we have nothing like that. There's no energy, there's no interatomic potential energy, which needs to know where the two different particles are positioned in space. So, I may give a short bit of time and devote towards that case a little later in this course. I don't know where to put it or how to do it, but it is an important case whenever to do the statistical mechanics of a group of particles when there is an interatomic potential, a force of attraction between them. But we're going to neglect that here. Okay, I think I got through all those. M is the mass of the particle. This is the potential energy. Again, the only potential energy we're going to really consider for our very simple cases is the one where the walls are in, there's infinite potential energy at the walls, but inside the box, the potential energy is zero. This term is, of course, called the kinetic energy. So it's the usual sort of case that you say the total energy per particle is equal to the particle's kinetic energy plus its potential energy in a certain field. Now, uh, if n is large, then we're going to do the same thing that we did in the discrete energy levels case. We're going to pretend that it's a continuous variable. Uh, but moreover, we're also we can't bin particles in discrete energy states anymore. So the way we take care of these things is we're going to use a particle density, okay, a particle density function, which is an idealization of reality. We're not counting particles in some volume of space explicitly. So I'll show you how this works. So let omega, so this is our box, or the open set describing the interior of the box, be a simply connected domain with a certain fixed volume. So we'll use this again and again. The volume of this, we could say the volume is L cubed, where L is the side lengths of our box, but that's not necessary. We'll just set the volume to be some specific thing, V. This is a positive number, and now it is important to keep track in this section more than ever before of units. So, what are the units of this? Well, for example, the units of this volume are meters cubed, for example, or whatever length you like cubed. The number density of particles, and this is how we're going to track states of our system. We're going to keep track of the number density of the particles. This is a function over this six-dimensional space, omega cross R3 into the non-negative numbers. And it's got to have the following property. It's got to be, I just said this is non-negative function, so its values are everywhere non-negative. It has to be integrable, okay? And because we've said it's already positive, that's the same as saying that it's integrable in the usual sense, okay? We don't have to write the absolute values there, though, because it's already known to be non-negative. So we need this to be integrable, and in fact, we need it to integrate to exactly n because there are exactly n particles. So this is like a true density. If I have this domain here in what we call phase space, if I could draw it, unfortunately, I can't draw this space. So a I have a coordinate representing space and I have a coordinate representing velocity. And so this guy, this potential, or not potential, sorry, this density is some function, right? Some function of phase space. Something which looks like this. And if I integrate that function over all of phase space, I get the total number of particles. Now, I put a peak here in the middle of this domain. So that means there are a lot of particles there, and relatively, and in other parts of the domain, there are relatively few particles. So we can think about we can think about particles being clustered in certain parts of the domain. Maybe all the particles are over near this wall, and so that would be the case where the function would have a peak there. Or maybe it's over in this location. So that density function would have a peak there. Okay, so anywhere where the density of particles is high, this function should have a large value, and where there are very few particles, this thing is very close to zero. So I hope that ugly picture portrays that. Of course, this normalization is exactly what we would want, what we expect, right? And all the particles should add up to n and always be be fixed, right? So this is the case where if I have particles in a box, then particles shouldn't get outside the box or shouldn't be injected into the box, and so the total number I have in there always stays the same. Now, notice something weird about this integration. So the integration over the physical space omega is just a three-dimensional integral 0 to L, 0 to L, 0 to L. But this density here, right, is a function of both space and velocity space, real space and velocity space. For this integral here, I have to integrate in three dimensions from minus infinity to infinity, minus infinity to infinity. So this is a triple integral, minus infinity to infinity. So if you look on this diagram, this v goes in, if this was one dimensional only, v could have positive and negative values, okay? But x might be confined between 0 and L. Okay, so just keep in mind phase space looks a little bit interesting. This is bounded, but this is completely unbounded. And what this represents is the fact that particles can have any velocity that we choose, right? So particles could be zipping around here in our very simplified model at twice the speed of light. There's nothing to stop them from doing that in our classical setting here. Now, this function is called the number density of particles. There's a companion to this, which we saw in the discrete energy levels case, called the probability function. And so we're going to have one here as well. So this function p, which is more or less exactly the same as f, is just a normalized version of f. Okay, so it's just F over N. P is F over N. And of course, if F has this normalization, right? If I divide both sides by N, then this function is going to sum to 1, or it's going to integrate to 1. Well, it's a probability density, right? And what does that probability density represent? Well, it's the probability that, this is some given function, and well, the total probability that the particle is in some state has to be equal to 1. But if I integrate over a smaller area, then I can find the probability that the particle is going to be in a certain location in physical space with a certain velocity range. Okay, so I could define the probability of being in certain states in state space by doing that. Do I do that down here? I don't exactly do it, but I can show you how that's done. All right, now, like we've done many times before, we're going to assume that there's a fixed and finite amount of total energy in the system that can never change, as well as a fixed and finite amount of particles in the system that can never change. So remember we had this per particle energy function that we defined earlier. That's got the energy information of our system completely. So if you tell me or give me a function f, what is f? F was our number density function above. It's everywhere non-negative, right? And it integrates to n. I'm going to define the total energy of the system, the integral of F times U over this space called phase space. And that has to be a fixed finite number U. So here's another thing you might need to worry about. Well, so this guy here is a integration over a finite domain, but this is an infinite domain, right? So I've got to be worried about the fact that this function will have to be integrable over the velocity domain. The way this is set up, by the way, we can assume that the u function is also going to be positive, right? So the if I go back to the u function, it's um, it's the kinetic energy of particles plus the potential. Now, the potential energy doesn't have to be positive, but we can assume that it is. In fact, we're going to make this go away eventually in the application that we want to use. Okay, so this integral has a positive or non-negative integrand that should integrate to some finite number. Okay, so remember, not all integrals are convergent, right? Some integrals diverge, and so we're going to sweep a little bit of that under the rug as we go along here. We won't worry about that so much. Now, remember, I kept calling this phase space. Let's give it a name because we're going to see it again and again. Q, which is defined as omega cross R3. This is the velocity space here. This is the real space coordinates. Q, omega cross R3 is called phase space. And of course, it's a subset of six-dimensional space R6. So now we can play a kind of game. If I have a subset of that phase space, then I can define the total number of particles in that subset. So this might be the subset of particles near the wall somehow with a certain velocity range. Well, I can calculate how many particles I expect to find in that subset just by doing this integral here. Okay, so if this is integrable over the infinite domain Q, then it should be integrable over any measurable subset of that. And likewise, I can calculate the energy of particles in that set, and the energy of particles is exactly equal to that. All I'm changing here is we're doing the integral over some subset, some measurable subset of phase space Q. And now I could also do a probability, right? So I could integrate the probability function over phase space, but only over the set A. And so that would give me the probability that particles are in the set A. I can define something called the average energy. So this is the total energy. The average energy is what? So the average energy would be, I could just divide this by n. But what if I divide this by n? I've got to do that to the integrand as well. It doesn't make sense to divide this by n. But when I do that, this just becomes the probability function. So I'll give this a name. U over n, I'm going to call u bar. Okay, so u bar is the integral over all of phase space. Um, integrand is probability times the energy per particle. And of course, I'm integrating over q. If I wanted to calculate the average energy in some set A, I would just restrict my integral to A. And of course, all I did here in getting this calculation is divide both sides of this definition, 11.4 by n. And so u bar times n is just equal to the total energy. Okay, so this is a formula that is sometimes used. The average energy times n is equal to the total energy. Now, let's have a look at this probability for just a second. What did we say about this probability function? We said, well, if you integrate the probability function over all of phase space, then you get 1. So what then are the units of the probability function? Well, the units of the probability function have to be the reciprocal units of phase space, okay, the volume of phase space. So the probability function is 1 over the units of the volume of phase space. What are the units of the volume of phase space? Velocity has units of meters per second. So this would be meters per second cubed, the the uh, the volume of the velocity space, and times the volume of real physical space. That has units of, let's say, meters cubed. Okay, so this is meters per second cubed times meters cubed, and then of course I invert it, so it's going to be seconds cubed over meters to the sixth power. So this is just what we call, this down here is what we call the volume of phase space. The volume of phase space. P has to have units that are inverse to that. Why does it have to have units that are inverse to that? Well, because we want the total probability to work out to be exactly equal to 1 and no units at all. So we need the units that we get via integration here to cancel with the units of P. But we had some uh, let's see. Well, actually, there's no real flexibility, I should say. And that's because when we define this number density, this guy has the same units because n is unitless. N has units of number. That's it. So, what are the units of number? Just unitless. So this f has the same units. It has to work out exactly that. That tells us that p has to have the same units, and all I've done there is normalize by dividing that previous equation by n. Okay, and so that tells us what are the units of the p function and also the f function as well. Okay, it's 1 over the volume of phase space, 1 over the volume of phase space. Now, I don't really care that they have exactly this unit, but you're going to see that we're going to be interested in knowing these units or keeping track of them ultimately. Now, the next thing to do is generalize our definition of the Gibbs entropy for the case that we have um, these infinite or continuous energy distributions, right? So the big difference here is that we're no longer assuming that energy can be in discrete levels, but has to be in a continuum of levels. So the Gibbs entropy, how are we going to define that? So for a system of n particles in phase space with the particle density F, The Gibbs entropy is defined in this way. So it's minus K Boltzmann, integral over phase space, Q. So, right, these are really six integrals. So there's three for space and there's three for the velocity space. Okay, the integrand is F log F over N. So in the case where we had just discrete energy levels, our F function was that N sub J, right? That was N sub J. It was already unitless. It just had units of number. And so when I canceled it, when I divide it by N, it's definitely still unitless. But we just said that P and F both have units of 1 over phase space. So I have to normalize this a little bit further because, we're careful mathematicians. And we know that if I take a log of an argument, that argument has to be unitless. So I have to put a unit normalization inside of here to make this argument unitless. So how do I do that? Well, I'm not going to tell you exactly what we need to choose for this value just yet. All I'm going to say about it is that it should be some positive number, and usually this number is actually taken to be bigger than one, and I'll tell you why momentarily. It's a positive number, and it's just a normalization factor set up so that this argument here, which is the same as, remember, f over n is just the probability function. So it's really just p over p naught, and that's why I use the symbol p naught. These arguments or this argument should be unitless. Remember, bracket is what I use to say what the units should be. Okay, so units of this should be just the same as the units of one, or in other words, unitless. And so that means that the P naught has to have the same units of 1 over volume of phase space. That's because it has to cancel the units with P. They have to have exactly the same units. So if you want to think about it, this is somehow a bit like a further probability normalization, except that if you want to make the entropy to be a positive function, you should choose that. So we already know that this is going to be, this here number is a fraction, right? This must be a fraction because if I integrate f over phase space, I actually get n. So this must be everywhere some fraction. But if I'm not careful, then by dividing this number, this might not be a number less than 1 anymore. So that's the other caveat. I want the number that appears in here to still remain less than 1 in its total value for every point in phase space. Well, the easy way to do that is just to take p greater than 1, p greater than 1. So uh, we could even say it here, p is greater than 1. Okay, so some normalization, which makes everything dimensionless. And let's see, and makes this number here, keeps this number less than or equal to 1. Okay, so that's the Gibbs entropy. And why did we pick this form? Is there any guidance why we chose this form? The reason we chose this form is that it's exactly the same form as for the discrete energy case. So this is just basically the continualization or the continuum limit of the discrete energy case. Before we had minus K Boltzmann out there, same. We had a summation over the number of energy states. Now, we don't know exactly what those energy states look like. We have to integrate over phase space to get the energy levels. So we replace the summation by the integration. Remember I said F plays the same role as NJ. And so NJ was there before, now it's F. Then we had log of NJ over N. And this plays a role of NJ. N is there. But then that begs the question, what's going on with this guy? And the reason we have this here is, well, it's just a normalization so that we can make sure that this guy, this whole fraction, is less than one. No, sorry, not less than one, is unitless. Okay. And we still want it to be less than one so that this minus makes sense. Now, that's not exactly true because we could shift our minimum entropy value a little bit. But if you want the minimum entropy to be zero, then this becomes an important normalization. Its actual value. We can define, as we did before, the average entropy per particle. And the way you do that is you just take the Gibbs entropy and you divide by n. N is not changing, right? It's always fixed. But the entropy can change um, uh, depending on how the state changes. So this is F tells me what is the state of the system. And so as this changes, the entropy changes. And so the thing we'll be looking for is the same thing that we looked for in the last two lectures. We'll be looking to maximize this entropy subject to constraints. Okay, this one has a nice symmetry. If I look at the average entropy per particle, it has a nice symmetry because it's P here and P here. I've always liked that one. Um, and so, yeah, it, this is something you can use if you find it useful, and otherwise we don't have to worry about it. So that's the average entropy per particle. And again, we're always making sure, at least as often as I can remember to do so, to make sure that the arguments of the transcendental functions like log are unitless. So log is a little bit of a tricky one, and that is because remember the if I take the log of a product, that's the sum of the two logs. And similarly, the log of a quotient is the difference of logs. So I can always, through an additive constant, change the argument. Um, so it doesn't change things kind of fundamentally, but I do like to keep track of that. Now, once we get to the so-called continuous partition, the continuous energy partition function, we'll see that this normalization factor plays another important role. Okay, so as we saw in the discrete energy or sometimes this is called the quantized energy case. The equilibrium state is the one that maximizes the Gibbs entropy. And so that's what we're going to be looking to show here as well. So our next task is to maximize that Boltzmann entropy subject to constraints, the mass constraint and the total energy constraint, and see what we get. All right, so the equilibrium particle density, theorem 11.1. Let's see, I think I numbered this theorem wrong. I think it should be, yeah, I've already got 11.3, so this should be theorem 11.4. Okay. The equilibrium particle density for non-interacting particles with the following constraints. The total number of particles must be fixed at n, and the total energy must be fixed at U, is given by the so-called continuous Maxwell-Boltzmann distribution. Okay, so look at the form of this and see how it corresponds to the form that we had previously for the discrete energy or the quantized energy case. So the Maxwell-Boltzmann distribution is, again, an exponential function minus beta. Beta is a Lagrange multiplier. And the way we can find that Lagrange multiplier is ultimately solving or imposing the fixed energy constraint. So minus beta times the density, or not the density, but the per particle energy at x and v. So notice this is no longer discrete. It's complete continuum of energy levels divided by the Boltzmann constant. Remember, So the Boltzmann constant is just a constant which sets the temperature scale. We know that the entropy has to have units of energy per degree of temperature. So the Boltzmann constant is just the thing which sets those units. If we want to use the Kelvin scale, then the Boltzmann constant has a very specific value. Now, the that normalization, that probability normalization constant comes in P naught. This normalization was in our previous one, n over z. Z is again the partition function, n is the total number of particles. And the partition function is given by this definition. Okay, so our normalization so that we can satisfy the mass constraint satisfies this. Z, the partition function, has to be unitless for things to make sense. So let's check its units. Exponential of a unitless number is a unitless number. Okay, so this doesn't have any units on it. If I integrate that, then I get the units of the phase space. So I need to multiply by, or that I should say, the units of volume of phase space. So to normalize this so that it has no units, I have to divide by the units of volume of phase space. And so that's exactly what that um where am I here? Right here. That's exactly how we chose the units of this. We didn't set the value. We said the value we want to, let's just make it bigger than 1 so that this minus makes sense and this is a fraction. But we didn't set them otherwise. We didn't set those units. Actually, quantum mechanics tells you how to set those units. Okay. All that we need to know now is that we need some units for phase space. We need to have some normalization factor, which it's P naught, which has units of 1 over the volume of phase space. As I said, beta is a Lagrange multiplier that can be uniquely determined as a function of u and n. But I don't say how, and I don't prove this. We merely suggest that it's possible, and then we move on. And we did the same thing when we were talking about the discrete energy levels case. So let's prove this. How we do this is the same way we did it in the discrete energy level case. So first of all, we minimize instead of maximizing a functional. So we minimize minus the minus of this, which is just minus the entropy. Okay. So I just removed the minus sign here. So I'm going to minimize rather than maximize. I'm just happier minimizing. I'm not sure why. And so here's the entropy, it's minus the entropy function, and this is my constraint for the total mass, and this is my constraint for the total energy. Okay, so this constraint wants to keep the total energy fixed to U, and this one wants to keep the total number of particles fixed to N. Um, Now, just to make life a little bit simpler, I'm going to start replacing that any anytime I see X and V, I'm going to replace that with the variable Q. So Q is just my variable for generically a point in phase space. So it's got coordinate of X, a coordinate of velocity. So this is a six-dimensional vector. Alpha and beta, of course, are Lagrange multipliers that have to be determined. And the way you compute to find the minimization of this, you can't use the gradient anymore. You have to use a technology called the variational derivative. So, um, how many of you guys, maybe by a show electronically of hands, have seen the variational derivative? You've talked about it in your class on maybe optimization or calculus of variations. But it's entirely analogous to the gradient. So remember, we if we have if we have a vector, let's say, and I want to find the gradient of a function of that vector coordinate. So for example, x plus sy, that's our vector coordinates. Then if I set s equals 0 in this calculation, I can show that that's just going to be the x gradient of j. Okay, so this is going to be a gradient, right? That's a vector dotted with y. And if I take a time derivative, suppose that I have, or a tau parameter derivative of j, which is a function of x, which is itself a function of tau. All right. So what does this work out to be? This works out to be the x gradient of j dotted with the tau derivative of the vector x. Okay. Either way you do this calculation, these two objects come out to be the gradient. So we used this a number of times previously. So this is just kind of a way of saying what the gradient is. Now, in this case, where our function is actually what's called a functional, it's a function of a function, it's an integral of a function, then we have to do things slightly differently. We're going to use the same or a similar technology, or I guess the better thing to say is an analogous technology. So we're going to do it like this. Um, we'll make a perturbation of that. Say I use G here. And then we're going to take the S derivative of that and then set S equal to 0. And so what we'll find is that this is going to be equal to the integral involving J. J is defined as an integral. I should say that an integral which is used in defining J. Say it better that way. And then we're going to get an object called the variational derivative of f with respect to f, or of j with respect to f, times g. Okay. Or if I have a situation like this, where j is a function of f, which is a function of tau, then I will get the following and when I do the calculation. And this will be the tau derivative. Yeah, tau derivative of f. I should write this as okay. Either way I do it, whatever I find to be in this spot right here, when I do this calculation, either this one or this one, whatever I find to be in this spot has to be the variational derivative. So the variational derivative is the analog of the gradient. And the way I find the equilibrium or the extremal value for this function is to set the variational derivative equal to 0. So that's what I'm doing here in finding the minimum of the function j. Remember, I'm using minus the entropy. I'm trying to maximize the entropy. It's the same as minimizing minus the entropy, subject to these two constraints, which are taken care of by the Lagrange multipliers. But the whole thing is given by an integral rather than it's a functional, not a usual function of a vector. So I'm going to use this variational derivative technique that I hope that some of you have seen in, as I said, calculus of variations or optimization or in some other course. And what I do, what I find when I do this calculation is I'm going to get G and then times some other stuff. So this other stuff is what I'm going to isolate, and I'm going to identify that with the variational derivative. That's the rule. Okay, that has to be the variational derivative. And this has to be equal to 0 at a extremal value of the J functional. And I should write this as, just to be clear, J is not a function, it's a functional. Okay, so I usually use brackets with functionals. So to find the extremal value, I'm going to set this equal to 0. Okay, now this has the Lagrange multipliers built into it. I didn't go through this calculation. I'm going to leave that as an exercise for you guys to show that this actually leads to this. I get this expression for my Lagrange multiplier. I need to set this equal to 0. By the way, the variation should be 0, okay, at the equilibrium point. And there's a little lemma which says that, well, if this is generic and this has to be equal to 0 for any generic value of g, then it must be that this part of the integrand has to be the one that's zero. So that's how you get that the variational derivative should be equal to zero, in case you've never seen it before. Now, all I have to do here is solve for f, and it's doable. All I need to do is invert the log. Inverting the log, I get exactly this. Um, this is a unitless number here again. I've taken pains to make sure that my beta parameter, um, eh, my Lagrange multiplier, when I multiply it times energy, has the same units as K Boltzmann. Or in other words, K Boltzmann over the beta parameter has the units of energy, so that cancels. So this is unitless. That's good. Um, and yeah, this ha what now this will have units. So what units does it have? It has units. This is unitless here because my partition function is going to be unitless and is going to be unitless. This has P has units of 1 over the volume of phase space. Okay, Z, my partition function, this is the normalization which guarantees that we have our mass constraint. So I'm not redoing all these calculations, and the reason I'm not is because all of this is quite similar to what we had in the quantized energy case. Okay, it's really quite the same. So when I use the constraint 11.8 to normalize the this value, that sets the value of z to be exactly equal to this. Now, we need to check that z has no units. We've already done this, right? So this has no units. So this has to have units that are inverse to the units here. These are units of volume of phase space. So this is has volume. This has units of 1 over volume of phase space. Okay, so now we've eliminated the mass constraint. So alpha is gone in our solution, but beta is still present. How do we get rid of beta? So the way we get rid of beta is the same technique that we used previously. So I'm going to end the proof of that last one by simply saying that beta can be found. It's a function of u and n. It's unique. And that's all I'm going to say about it. The next proof is actually, the next calculation is actually going to show you how this is done. Okay, how this goes about. All right, so this again, I'm off on my count here. This should be 11.5. Not sure how I got off on the count, but it happens. 11, theorem 11.5. At equilibrium, the Gibbs entropy satisfies this equation. Now, what do I mean by the Gibbs entropy at equilibrium? This is a concept that we talked about last time as well. The equilibrium value, remember, entropy is defined not just for equilibrium, but for any state. It's defined for any state. The equilibrium entropy is the entropy at the equilibrium state that we just calculated. Okay, so this gives an expression for the equilibrium entropy function, and it's just a function of u and n, not a function of anything else, at least at the moment. And so what we want to show with this theorem is that that's exactly equal to beta times u. This already is going to tell us that beta, again, that beta is a function of u and n, or it's going to corroborate that as evidence, plus K Boltzmann log z times n. So this is actually just a kind of Euler equation. So you remember the Euler equation that we derived back in the setting of classical thermodynamics? This is exactly an Euler type equation. This is something times the internal energy. So that is another indication this has got to be 1 over temperature. And then something times the number of particles. So this should be chemical potential divided by temperature. At equilibrium, the derivatives of this function here there are only two variables, right? U and n. So the the derivative with respect to u should give me beta, as we'll show, and the derivative of the equilibrium entropy with respect to n gives me this term. Okay, so I may have to go, for the sake of time, through these a little bit quickly and just have you check them on your own at your leisure. But we can do this one fairly easily. This one takes a little more time. But nicely, the calculations are completely analogous to what we did for the quantized energy case. So at equilibrium, we have the Maxwell-Boltzmann distribution. So this, of course, is the so-called partition function. So all we're going to do is we define this as that entropy at the equilibrium state. So plug in the equilibrium at state for the Gibbs entropy function and turn the crank. Okay, so we've got an exact expression for all this stuff. Just put it in here, put it in here. And lo and behold, at the very end, you get this. Okay, so details, I'm not going to go through those. Okay, similar calculation to what we did before. Please do, when you're reading this on your own, check that we haven't made any errors. Pretty sure that it's error-free, but I'm not positive. All right, now what we're going to do is suppose that our number density of function can change via process parameter. So I'm going to think about this being a function of phase space and of a tau parameter space. Okay. Now I don't this tau parameter space doesn't have to be infinite, it doesn't have to start at zero. I can start with whatever I want. But basically, as I change the tau parameter, I get different values for my number density of particles. No matter what, I'm going to make sure that this is normalized so that along that process path and for the process parameter tau, I'm always have, well, I guess um, this guy doesn't have to be exactly equal to the same n that I have above. This is a function of tau. But whenever I stop at the equilibrium point, I want this to be exactly equal to the same n that I had previously. But notice how this changes as a function of tau because this is now a function of tau. All right, now I'm going to, for a generic process path, I'm going to differentiate the Gibbs entropy with respect to the process parameter. I'm going to skip down to the end because all this is we plug in that number density of particles, take the tau derivative and see what we get. So what we get is this thing here. This is exactly analogous to what we got before. We got a summation before. This was n and this was n here. This n dot, what does this represent? This represents the tau derivative of f. It's just a shorthand notation. And I also use the notation up above in this calculation, the n dot, that was equal to the tau derivative of the total number of particles n. All right, now to finish this calculation out, I need to, let's see if I can explain how this is going to work now. So now I need to say how can the energy change? Well, remember the energy levels, this energy functional, just like the or energy function, just like the energy levels previously, is a given function. And so this can't change with tau. So the only way that this total energy changes is as I change f through so this is a generic path through the number density space, parameterized by tau, and so um, that changes the value of the total energy. If I take the tau derivative of energy, I'm going to call that u dot in analogy with what I have up above, and that or tau derivative just moves in and attaches here. So this gives a partial derivative f with respect to tau. Okay, so put that into your pocket for just a second. This is a generic path through number density space. I'm going to assume that when I stop at the parameter tau naught, I get the equilibrium density. So what is this equilibrium? This is just the Maxwell-Boltzmann distribution. Okay. So what I want to do is I want to repeat the calculation that I did above, but now I want to stop at tau naught and see what I get. So this calculation is quite similar to what we had before. What you get is what is in front of this variable here, u dot, is beta, and what is in front of, I guess, n dot should kind of go out here, is k Boltzmann log z. What does this mean? Well, since I'm really taking the tau derivative of my entropy at equilibrium, this means that I've actually found the derivatives of the equilibrium entropy function, and they are exactly whatever multiplies the u derivative is whatever multiplies u, and that's beta, and the n derivative is whatever multiplies n dot. Okay, so that's k Boltzmann log n. This allows me in an analogy with what I did before to define the statistical temperature. And that's because the statistical temperature should be the same as in the classical case. We had an expression for equilibrium, and I said that when we take the derivative of that with respect to u, we're going to call that 1 over the temperature. Okay? And so if you like, the temperature is just 1 over this derivative. The equilibrium, of course, is defined as usual. It's just the Gibbs entropy at the equilibrium Maxwell-Boltzmann state. And we're going to call the statistical chemical potential the same as what we would have called it in the classical setting. We're just going to set that equal to the derivative, I should say the chemical potential over temperature is the derivative of the equilibrium entropy over the derivative of equilibrium entropy with respect to the number of particles. All right, so if I define them that way, and I know that these derivatives are given here, that immediately tells me that beta is equal to 1 over the temperature. And it also tells me that the chemical potential is equal to k Boltzmann T times log Z. Okay, so you can check the details of that. Okay, so just 1 minute left. We're almost done, so this is good. So what does this say? Well, first of all, it tells us that the 1 over the beta parameter, our Lagrange multiplier, is exactly equal to the temperature. It tells us how to find the chemical potential in terms of the partition function, so that'll be useful. Now, the temperature, therefore, is a derivative of right? It's a derivative of this function here. So that means that this is going to be a function of u and n, because this is a function of u and n generically. So temperature is a function of u and n, so is the chemical potential. But now what we want to show and what we want to have happen is that we can always invert this temperature energy relation. So this is a very important point about what we do in statistical mechanics and in classical thermodynamics. And it really has to do with the fact that we're assuming or that we're able to show something about the concavity of the entropy with respect to the energy. So we're always going to be able to, because of that, to invert this function. So we can always find U, the total internal energy, as a function of temperature and N. Okay, so we're going to use that again and again, especially next time as we study the ideal gas law. So I'm going to stop there and I'll take any questions you guys have.